So, hello and welcome to this lesson on our study of mathematical biology 2. So, this happens to be the second lesson, and in this lesson, we will talk about the Verhulst logistic model. Okay, so the Verhulst logistic model. So, note that in our first video, we talked about the multi-chain model. All right, so we are building on that and to introduce the Verhulst logistic model. So, when it comes to models for single population species, right? And the Malthus model is the basis, it's the simplest of it all. Okay. Then, based on the multi-chain model, we built on it to get the Verhulst logistic model. So, let's see how it was done. Okay. So, let's take a quick intro. So, Malthus observed that the population grows unboundedly for a long period of time. So the keyword unboundedly here is very, very important. So the unboundedly means that when a population starts to grow for a long time, it grows without any limit. So based on the model Malthus proposed, that was the interpretation of it. But in reality reasoning, this is unaccepted in the scientific community because growth has a limit, it has bound. So the reason why it is unacceptable is because population cannot be supported by the available resources for a larger or a longer period of time. So as a result, the population will decline or meet an equilibrium, right? So you see, when the population is growing, it will grow to a certain limit that it can't grow again, right? When it reaches its maximum capacity, which in biology we call the carrying capacity, it can go over that one. It can't go beyond that. So in order to overcome the shortcomings of the Malthusian model, a Belgian mathematician called Verhulst in 1838 modified the Malthusian model by inculcating a carrying capacity. All right, so the carrying capacity introduced a limit onto the Malthusian model so that this time around it's not going to grow unboundedly. I hope you get it. So what is carrying capacity? So the carrying capacity is what the environment can support. Okay. So for instance, when you take a cattle in a pen, the field degrees on is their carrying capacity. So that means that if the field degrees on, if let's say the grass is finished, they will begin to die, right? So population doesn't grow unboundedly. It's reached a certain point and it becomes stable. That's what we call the equilibrium point. Okay, so when it reaches that point, it becomes stable. So it can't go beyond the carrying capacity. So now let us see how to derive the logistic model. It's very simple. So in our previous video, we learned how to derive the multi-chain model, and we had this. Okay. So what Verhulst did was that from the multi-chain model, he just introduced this factor 1 minus p over k to multiply the right hand side of the multi-chain model to obtain this equation. So you can see this is the multi-chain model, but he just multiplied by this and we had the logistic model. So equation 1 is what we call the logistic model, okay? And the R there is the intrinsic growth rate or the per capita growth rate, and the K is the carrying capacity, okay? All right. So this here is the logistic model. So now that we have the logistic model, let's analyze it, okay? And we are going to analyze it qualitatively and using analytic methods. Okay, so let's first take the qualitative method. For the qualitative method, we'll be interested in finding for fixed points and discussing stability. So from it, we have dp dt is equal to rp times 1 minus p over k. Right, there's the logistic model. So we have to find for the fixed points of this model. So find for the fixed point, what we do is that we set the derivative to what? 0. So we set the p dt to 0. And that will give us rp times 1 minus p over k is equal to 0, right? And here we can say that rp is 0, or 1 minus p over k is 0. So when you solve for p here, you get 0. And when you solve for p here, you get k. So it means you're going to have two fixed points, 0 and k. Right, those are the two fixed points. So now what we are going to do is we are going to discuss the stability of these fixed points to know which of them is stable and which of them is not. So to do that, we had this to be the right hand side of our model. Okay, so we let any function represent that. So let's call that function f of p. So we let f of p be equal to rp times 1 minus p over k. When we multiply it, we are going to get rp minus rp squared over k. So this is f of p. So what we do is that we take the first derivative of f of p with respect to p, right? So when you do that, you're going to get r minus 2rp over k when we differentiate with respect to p. So after getting this, what we do is that we put in a first fixed point, we analyze our results, we put in a second fixed point, then we also analyze our results. Okay, so the first fixed point is 0. When we put in 0, we are going to get r minus 2r times 0 over k, and that means this place will vanish and we just get r. And r is the intrinsic growth rate, which is positive. Okay, so r is greater than 0, and since r is greater than 0 here, it means that our fixed point 0 is unstable. Okay, then we go to the second one, that's the second fixed point, which is k. So when we put k inside f prime of k, we get r minus 2r k over k. This will give us 1, right? So we get r minus 2r, which will give us minus r. And since the result here will be negative because r is a positive number, right? It means that the second fixed point is asymptotically stable. So what is the interpretation of what we just did? Okay, so maybe let's see. Let me just draw a diagram here. So let's say when the population, let's say we have something like this. So let's say this place is 0, and this place is, let's say, k. So what we can say is that when the population is at 0, it's unstable, so it will continue to grow and grow and grow and grow and grow and grow. But when it gets to 0, right, because when it gets to k, sorry, because k is a carrying capacity, it stabilizes there. It becomes stable over there. So what we did, that's how we can interpret it. When the population starts to grow, it grows until it gets to the carrying capacity. Then it stabilizes around our place. So that's the reason why for the fixed point p star equals k, we had it to be asymptotically stable. Okay. So that's where the qualitative solution. So now let's go to the analytic solution. So we have the dt equals rp times 1 minus p over k. And this differential equation is autonomous. Do you know why? Okay, it's because you see the independent variable here is t, and with the right hand side we don't have t there, so that's the reason why this is autonomous. Okay, so we can solve this differential equation analytically using the method of separation of variables. Okay, so we have dp dt equals rp times 1 minus p over k. So when we divide through by p times 1 minus p over k, we'll get this, and we can do some small simplification here to get this, right? And we can further do what we have here to get this. I hope you should understand by now. This is some simple algebra. Okay, so you can take your time and do it till you get to this place, which is quite simple. Okay, so after doing this, then we have to integrate both sides. Okay, so that gives us this. And because we are integrating with respect to p, we can bring our key outside here and we get this result. But you can see that when it comes to the denominator here, it is p times k minus p, right? So since we have factors over there, it will be very good if we can resolve these into partial fraction before integrating. So when we take the 1 over p times k minus p. Because it has linear factors, resolving it into partial fraction, we'll get something of this form, right? Then our aim is to find a and b. So when you multiply through blah blah blah, we get 1 will be equal to a times k minus p plus b times p. So at p equals 0, we get 1 will be equal to ak. Then a will be equal to 1 over k. And at p equals k, we get 1 will be equal to a times k minus k plus bk. So then we get 1 will be equal to bk, and b will be equal to 1 over k. Right? So now we can make substitution, and we will have this to be 1 over k p plus 1 over k divided k minus p. So since 1 over k is a common factor, we can factorize that one out, and we get something of this form, right? So the whole of this is now this. So we go back here, and when we see this, we make substitution. So that will give us this, right? Is equal to this. Fantastic. So we can bring the 1 over k outside as well. So when you bring that one out, you're going to get this k over k. Then we have everything here. Then k over k will cancel and give us 1. So that means since the integral is also a linear operator, we can expand. So we'll have integral 1 over p dp plus integral 1 over k minus p dp, which will be equal to integral r dt. Okay, so when we integrate 1 over p dp, we are going to get ln pt. And when we integrate 1 over k minus p dp, we get minus ln k minus p of t. And this is how we got it. Okay, so you see we have integral 1 over k minus p. So we are going to use substitution method here. So we let u be k minus p. So du dp, when you differentiate with respect to p, you get minus 1. Then that means that dp is equal to minus du. So now this problem will become minus integral 1 over u du, right? We've changed it to u. And when you integrate this, you get minus ln u, right? But now we said ln was what? U was k minus p. So when you put that one inside, we get minus ln k minus p. Okay, so that's why this is this. These are indefinite integrals, so we can bring c to it and c to it, but because of this right hand side, we can decide to hold on with this. Alright, so that means when we integrate, we'll get ln pt minus ln k minus p to be equal to rt plus c. When we integrate the right hand side, we'll get rt. Then we bring the constant there. Okay, so plus c. So that's equation 1. So from now we have to find c. That is the constant. Okay, but at time t equals 0, the population p of t is equal to the p naught, right? So you're going to use that to find for c. So wherever you find t, you put 0 there. So you get ln p of 0 minus ln k minus p of 0 is equal to r times 0 plus c. So that this one will go away because r times 0 is 0. Then p of 0 is p naught. So we'll get ln p naught minus ln k minus p naught to be equal to c. And which implies that c is equal to ln, laws of logarithm. Ln a minus ln b is ln a over b. So we can write this in this form. And that is our c. So now we can put our c back into equation 1. So when we do that, we are going to get this. Then now we have to rearrange things here to make sure we get our p of t. Okay, all right. So we can also write the left hand side here as ln p over t over k minus pt. And I know by now you know why. So this is equal to rt plus ln p naught over k minus p naught. So we can bring this to the left hand side and we'll get this, right? Then we can combine them to get this. This is very simple. Okay, so now let's simplify what is inside. Okay, so that's what we have here. P over t over k minus pt divided by p naught over k minus p naught. So this is the same as p of t over k minus p of t times, Yes, minus p naught goes up in p naught because we have the times here. And this is simplified as this. Okay, so when we put it inside, then we'll get this is equal to RT. I hope you get that. All right. So now when we find the exponential on both sides, the lane will go away, and we will have ERT for this side. So that's what gives us this. Okay, but we are still finding for what? P of t. So we can multiply through, can cross multiply. We have one here. So when you cross multiply, we'll get this. And when we simplify the right hand side, we'll get this. And since we are looking for P of t, we can group terms containing P of t at one side. So we have P of t here and P of t here. So we can bring all of it to the left hand side. And that gives us something like this. Then we can factorize that one out. So when you factorize P of t out, we'll get this. And this is equal to this, right? So when we divide through, we get P of t will be equal to K P naught E RT over K minus P naught plus P naught E RT. So when we get here, we can decide to divide through by P naught ERT, okay? So when you divide through by that, we'll get something like this, okay? Realize that this will cancel this. This will also cancel this. And we'll get K over K minus P naught over P naught ERT plus 1, okay? And this can be written as K over 1 plus, so K minus P naught over P naught, then E minus RT. I hope you get this, all right? So this happens to be the analytic solution to the logistic model, and it's very simple. So this equation is the equation which is used for estimating the population at any time t when you are given your carrying capacity k, the initial population p naught, and the intrinsic growth rate r. So now let's look at the long-term behavior of the logistic model. So we have this to be the analytic solution, right? So as time grows, for like as we allow time to grow for a very long time, what happens to the model? So you can see that we take the limit as t approaches infinity. So as t approaches infinity, we have something like this, and this exponential function here, when we have a larger value, infinity is a very large value, it will be 0. So that means the whole of this will be 0. When you multiply 0 throughout, we get 0 for that part. So we get k over 1 plus 0, which will be k. So that means that as time grows, okay, the size of the population is equal to what? The carrying capacity. That means that the population doesn't grow unboundedly, but it is limited by what? The carrying capacity. And that was what he wanted to do. And you can see that we've been able to analyze it and see that, yes, he was able to do what he wanted to do. Okay. So the interpretation is that as time increases, the population gets closer to the carrying capacity and cannot go beyond it. The logistic model is very, very nice and very, very effective and efficient. So now let's solve some examples on the logistic model. Okay. So we have a question. It says use a logistic model with an assumed carrying capacity of 100 times 10 power 9, an observed population of 5 times 10 power 9 in 1986. So that means that's the, so this is our key carrying capacity. This is our P naught, initial population. And an observed rate of growth of 2% per year when population size is 5 times 10 times 10 exponent 9 to predict the population of the earth in the year 2000. All right, okay, that's great, that's great. So that means that the intrinsic growth rate here is 2%, right? So this is the data we can get from the question. Our carrying capacity k is 100 times 10 power 9. Our initial population p naught is 5 times 10 power 9, And the intrinsic growth rate is 2%, which is 0.02, because 2% is 2 over 100, right, which is 0.02. And then it says we should use this information to predict the population of the Earth in the year 2000. So you can see that the initial population was given in the year 1986, and we are finding the population in the year 2000. So the time difference would be 2000 minus 1986, and time is what, 14. So that means if this is p naught, then we are finding p of what, 14. So after 14 years from 1986 will be 2000, what will be the population? I hope you get it. So then we are finding for the population at t equals what, 14. So you know this formula already, we just derived that. That's the analytic solution part, right? So we quote it. Then you know, when you have your formula, it's very simple. You just make substitution, you put in your values. So this is the carrying capacity, the initial population, then this is our r, this is our t, 14. So when you put it inside and you make your computation, you will get the value here, 6,510,462,830. So this will be the predicted population of the Earth in 2000 from the data we had from 1986. Okay, so you see, it's very simple if you know the formula to use and you understand the various variable parameters in a question. So let's take a second example. After that, I also give you some trial questions with answers, then you solve it and you compare with them. Okay, so the question 2 says, show that for a population that satisfies the logistic model, the maximum growth rate of population size is rk over 4 attained when population size is k over 2. So solution, from the logistic model we have this, right? So we represent the right hand side with f of p. So when you multiply through, we are going to get f of p to be rp minus rp squared over k. And the power of p here is 2, right? So we have a quadratic equation. And when we have a quadratic equation of the form as squared plus bs plus c equals 0, this attains the maximum at the point s equals minus b over 2a. So comparing our quadratic equation to our function f of p, our a, which is the coefficient of p squared, is minus r over k, and our b, which is the coefficient of p, is r. So when we use this relation here, that means you are going to get p to be equal to minus r over 2 times minus r over k. The negative will cancel out, and we get rk over what, 2r, and this will give us k over 2. So yes, we have shown that the maximum rate is going to be attained at k over 2. So now let's find the maximum rate and see if it is indeed rk over 4. So you know that this is our f of p, right? So now we find p to be k over 2. So wherever we find k, wherever we find p, we'll put k over 2 in this function here. That's what will help us to achieve that. So we get p max k over 2 will be equal to r. There was p here, but now we put k over 2 there, minus r. P squared now become k over 2 squared over k. Right? So when you simplify, you get rk over 2, and you get rk squared over 4k because of what we have here, right? So k will take one of this, and this will give us rk over 2 minus rk over 4. And when you simplify this, you get rk over 4. So yes, we've been able to show that. So that's the solution to question 2. Okay, all right. Then I have some trial questions for you. The first one says, suppose the population satisfies a logistic model with r to be 0.4, k to be 100, and x of 0 to be 5. Find the population size for t equals 10. So when you solve this, you are supposed to get 75. You will get 74 point something, okay? And we are looking for the population. So 74 point something means we have to approximate to the nearest whole number. Like, you get it, all right? Then the question 2 says, suppose the population satisfy a logistic model with carrying capacity 100 and that the population size is 10 when time is 0 and 20 when time is 1. Find the intrinsic growth rate. So you are finding for what? R. When you do your calculation, if you're able to do it well using the formulas that we have, you are going to get 0.8109. Okay, so thank you very much for staying with me throughout this video, and I hope you now understand the logistic model and how to use that to predict um, the population. Okay, so don't forget to subscribe to the channel and like the video if it helps you. So in our next video, we'll talk about harvesting in population models. Okay, so what if we have a population we want to harvest some? Which model can we use to predict um, what we should take and a whole lot of things? Okay, so that's what we'll be doing in our next lesson, harvesting in population models. So thank you once again and see you in the next video.